In earlier videos, we looked at limits and how they work, and here's another method of solving it in our famous problem position here. So what we're looking at here, what is the limit as x tends to 0 of sine of x over x? Well, the limit of sine of x as x tends to 0 is 0, and the limit of x as x tends to 0 is 0. So I've got one of those 0 over 0 setups. And we looked at using Taylor before, but now we're going to use a method which a guy called L'Hopital, some people call it L'Hospital, whatever, Frenchman, L'Hopital, and we're going to do a bit of a proof using Taylor series, and then we're going to use it in practice. Okay, now sine of x over x. This is our example, 0 over 0. Now, if we have a look at the graphs on the left-hand side, here's my sine of x graph, here's my x graph. So this is going to be my f of x is in red graph. G of x is the denominator, and that's going to be my blue graph. You can probably see that along here, or these points here, are on this, almost on this straight line, so the values are the same for the two functions, so the answer is going to be 1, isn't it? Because the gradients are both 1 there. So we probably know that that's the answer we're going to. How can we prove it? Well, what we're going to do is we're going to replace sine of x and x on the bottom. We would replace them with Taylor series around where we're working. So if I looked at the numerator, well, f of x is going to become f of a plus f dash of a multiplied by that my little delta x there, that's x minus a. What would happen to the denominator? Well, that's g of a plus g dash of a times my delta x, yeah? And if I'm in this situation where f of a and g of a are both 0, that's this setup over here, isn't it? That's 0 over 0. I've got a 0 over 0 here. So both these terms are 0. So I just get left with these second terms, don't I? And if I look at those second terms, well, those two are going to cancel. So I just get left with this bit. So therefore, if the f of a and the g of a, where we're working, equals 0, then the limit of f of over g is just going to be the differentials at that point. So we just need to calculate them. So let's do that with our example. There's our example. My numerator is going to be f of x, so that's sine of x, and my denominator is going to be g of x. It's going to be x there, isn't it? And if I just re-verify, when x equals 0, well, the numerator is going to be 0, and when x equals 0, the denominator is going to be 0. That means I can use my L'Hopital rule, and if I get in there and do a quick go back and do my differentiation, if I take my function from up here, that's sine of x, I differentiate it, I get cos of x. I've got g of x, oops, that should be a 1, g dash of x is 1. So if I now sub it in for the values, we're working around x equals 0, so cos of 0 is 1, f dash of 0, cos of 0, which is 1, g dash of 0 is 1. So what have I got? Well, I've got the differentials here. I've got cos of 0 over 1, which is 1. So what's that tell me? I've just proved that the limit of, the limit of those, the limit of sine of x over x, whereas x tends to 0, is 1. Okay, let's have a look at some other things we need to watch out for. What happens if these two values are tending to infinity? So what's the limit of ln of x over 1 plus x? So if I put those values in at x equals 1, well, the top one's negative infinity, the bottom becomes positive infinity. I've got a problem, haven't I? Because I've got infinity over infinity, and I don't want that. Well, I could rewrite the top as being 1 over 0 and the bottom as being 1 over 0. So how am I going to do that? Well, I'm going to find reciprocal of f, I'm going to find reciprocal of g, and if I put those into there, then f of x over g of x is going to be q of x, because those are reciprocals, which is now going to be 0 over 0. And I know what the rules are for that I've just got to find the limit. And because, of course, I've got 0 over 0 for the q of a and the p of a. So once again, I come back to the setup where the first two terms are 0. I'm only left with these two. I can do that cancellation. So I can do that differential, q of dash over p dash, and I can prove, I'm not going to do it here, that that's going to be the same as f dash over g dash. So hey presto, I can use exactly the same setup if f of a and g of a are tending to infinity, whether positive or negative. So if that's true, I can use it. So I've got f of x here is ln of x, and if I just put x equals 0 in, I can verify that f of is negative infinity. The denominator is 1 over x. If I put x equals 0 in there, I get positive infinity. That means I can use the L'Hopital rule. So what do I need? I need to differentiate these functions. Well, the top function, ln of x, becomes the differential is 1 over x. The differential of g of x which is 1 over x, is negative 1 over x squared, isn't it? And I know that the limit of that, I could just substitute in my two differentials. Let's do that. So the top's 1 over x. That's the numerator. The denominator is negative 1 over x squared. If I simplify that, I just get negative x, don't I? With a bit of cancellation. And therefore, what do I want to do? Well, I wanted to find the limit as x tended to 0 of that function here, which is just minus x. And when x equals 0, that's a 0, isn't it? So the limit of x, as x tends to 0, of ln of x over 1 over x is 0. There we go. That's how we use it. One other nuance. What happens if we find that the gradients are 0 as well as the initial values? Well, if you think about it, using my trusty Taylor series, if I just take the first three terms, I've got f dash, so I've got f of a plus f dash of a times delta x, that's my delta x, plus f double dash x minus a squared over 2 factorial. Excuse me. I've got the same setup for the g's at the bottom. Now, if my initial values are 0 and my gradients are 0, then my first two terms here, that's going to be 0 here and 0 there, same on the bottom, 0 and 0. So basically I can ignore those as zeros. I'm just left with the third terms. There we go. There's my third terms. Of course, what can I do there? Well, I've got an x minus a squared top and bottom I can cancel. I've got 2 factorial top and bottom I can cancel. So what have I proved? I've proved that if my initial values are 0 and my gradients are 0, I can actually use the second differentials to find the value, f double dash of a over g double dash of a. So here's my summary page. Just to restate, if my initial values are 0 or they are tending to infinity, then I could use this formula here. And if I find that my gradients are 0 or tending to infinity, I can carry on and repeat the process, and rather than using my first differentials, I can use my second differentials, and of course I can carry on doing this repeatedly until I found something which is not 0 over 0. So I can find the fourth differential over the fourth differential, etc. So there you have it. Hope that's of use.